Hey guys, I just want to review the axe configuration with you guys, and then I would like to start talking about shapes. So last week we talked about the axe configuration. A, again, is the central atom, and there may be more than one of those, meaning it's not on the end or on the top or the bottom. X is the atoms that are attached to the central atom. So if there is a bond, that would be an X, right? So CH4 would be AX4. E is non-bonding electron pairs. So if you have a structure such as NH3, you have N attached to three hydrogens, and then you have a lone pair of electrons on the N. So that would be AX3E. And then little e stands for lone bonding electrons. And it's rare, but that it could show up on the AP exam. So after the axe configuration, so once you have your dot diagrams down, your axe configuration down, you can predict molecular shapes. So I'm going to take you through a couple of these slides, and what I'd like you guys to do is fill in your blank note packet along with us. So if you have two atom molecules, it's very easy. It's always linear. There's no axe configuration because there's no central atom. The bond angle is 180. If you have two domains, and again, to review domains are either a bond, double, single, triple, that would be one domain, or a lone pair of electrons or a single electron. So this has two domains. There's two bonds. The axe configuration, hopefully you can figure it out on your own, would be AX2, and it would also be linear with bond angles 180 degrees. When you have three domains, boron on occasion would be the central atom, you have a structure that looks like this, kind of like a propeller. So the axe configuration would be AX3, so three total domains. The geometry, which again, you have to memorize these geometries, would be trigonal planar. So planar meaning it's all on the same plane. And then the bond angle is 120. Now, also this one, right, has three domains, but I took a bond off and now I have a lone pair. There's still three domains. The axe configuration, however, has changed, right? So now it's AX2E1. The geometry of an AX2E1 is bent. The bond angle is a little less than 120 degrees. So what's happening is that these lone pair of electrons are more repulsive, so they're kind of squishing these bonds together. So what you need to know for the AP exam is you need to know less than 120. So if you say specifically 117, that's great, but less than 170 would be okay. And again, because of that lone pair. Okay, four domains. So this would be something that you learned in Regents chemistry, which was tetrahedral, right? Like a methane molecule. So you need to know those bond angles. There's four bonding domains on this one. Zero non-bonding. The axe configuration is AX4. The geometry is tetrahedral, and the bond angles are 109. Again, here we have four domains, but a bond is taken away, and now it's a lone pair of electrons, but it's still four domains. So this would be AX3E1, and I'm sure you guys know that. Okay, the geometry, which you need to know, is trigonal pyramidal. So this is like an NH3 molecule. So these lone pairs, again, are kind of squishing these together, and you're ending up with a trigonal pyramidal type structure. Bond angle, sorry, I can't, is less than 109, because again, these are more repulsive and they're squishing those together. So that's the VSEPR theory, right? Valence shell electron pair repulsion theory. Here we have four domains, but we took away another bonding site. So we have AX2E2. This would be water, right? So water has a bent structure, and it would be also less than 109 because these are also squishing the bonds closer together and away from one another more. Okay, now we're on to 5. So this is something outside of Regents chemistry, but it does happen, and actually much more complicated structures happen that we don't need to know about, but this we do. So 5 bonds, if you can kind of think of it as a trigonal planar, so you can see those 3 around there, and then we have a top and a bottom. So the top and the bottom are called the axial, and the ones in the middle are called equatorial. You don't have to know that though, but just kind of make sure you can know the bond angles as well as the name of the molecular geometry. So we have five bonding sites. This is an AX5, and the geometry is called trigonal bipyramidal. So trigonal bipyramidal. And the only way that you're going to know these is by practice. Bond angles are pretty straightforward. They're 120 and 90. Okay, so now we're going to be taking away some of the sites. When you're taking away sites on a molecule that has 5 domains, you start taking away from the plane first. So this is the planar part. So we have that. So again, what those are going to do is they're going to compress the bonds closer to one another. That's an AX4E1. This geometry is seesaw. So when I talk to you again in class and I see you in person, per se, I'll show you actual molecular structures of this, and you can kind of see the seesaw better, as well as the FET that we're going to be doing in a moment. Bond angles are 120 and 90, so they kind of all end up being the same with that. So they're all kind of repulsing one another, and they end up pretty close to that. Okay, another one, we're taking another one off the plane. And we have 3 bonding sites and we have 2 non-bonding sites. The X configuration is AX3E2. Our geometry is T-shaped, so it's just a T, which is kind of cool. And the bond angles are 180 and 90. So we're going to take another one off, and maybe you can kind of guess what this structure looks like. So we have 2 bonding, AX2, E3, and we have a linear shape. So you can actually have linear with all these 5 domains. Bond angles are easy, 180. Okay, lastly, we have 6 domains. So now we kind of have a square here. So this is a square planar, and then we have a top and a bottom, right? The axial. So this is 6 bonding domains and 0 non-bonding. This is an AX6. The geometry of AX6 is octahedral. So if you kind of put shapes, sides on all of this, it would end up being an octagon. The bond angles are 90. Okay, so now I'm taking it, when you have 6 domains, you take it off the top and the bottom, the axial positions. So I'm taking it off the top. And you can kind of see we still have the square planar here, right? And then we have the bottom one here. This one is called AX5E1, and it's called a square pyramidal structure. Bond angle still 90. So again, now we just took it off the top, so that would be in, you could probably figure out, I know you can figure out the X configuration. So this one is now we have just kind of a planar, so this is called square planar. And bond angles are 90 with that. And again, you'll be able to see that more when you do the simulation. Okay, and then lastly, I just wanted to talk about that odd electron, so that little e in the X configuration. So it is rare, but it does happen. It's called a free radical. And it just doesn't have as much power as a pair of electrons with respect to repulsion. So it's not going to condense these angles as much as it would if it was a pair. So NO2 is an example. So that is not nitrite, because nitrite has a charge on it, right? So that would be considered nitrogen dioxide, like carbon dioxide. So that would be the X configuration. The bond angle is weird. It's not quite as condensed as it would be for the one that had 3 domains. And what I mentioned last week is those often react. They're very reactive free radicals, and they often react with one another, and they create what's called a dimer. All right, and I guess I have one more here I want to go through. So here's an example of a molecule that has 3 domains, right? So it's got 3 central atoms. So you should just go ahead on your own and try to do the X configuration around this one, and around this one, and then go ahead and look at the answer. So this is the answer. And then from the X, you should be able to predict the shape of the molecule. So even though it looks like a straight line, right, when we write it on paper, it's actually the first molecule is tetrahedral, the second one is trigonal-planar, and the oxygen is bent. So you can draw it any way you want, linear, but you have to recognize that the structure is bent because it's AX2E2. Okay, so that's where I'm going to stop for today.